to time-dependent perturbation theory. Okay? Now, in the assignment that I gave you, we wanted to study some, so the system started from an harmonic oscillator started from the ground state, then it changed, so you apply time-dependent perturbation, and you wanted to know what happened after, so at large times, okay? So almost, I think everybody did it. Now, I think that all of you more or less got it right. So the probability that the system is excited after a large time, okay, then was this delta n1, okay, so only you go to the first, this was related to the symmetry of the Hamiltonian. There was something which I don't want to discuss, and then there was something like this, omega square tau square over 2, okay? Now, this is very interesting, because you see that, what is tau? What is the meaning of tau?
The period.
Meaning of tau?
Yes.
It's like the duration of the electric field, how long does it?
Yeah, so the field did like this, okay? Huh? So this was essentially the scale tau. Now you see that if tau becomes very large as compared to, you know, the inverse frequency, the 1 over omega, then you see that the probability to excite the system goes to 0.
It was exponent multiplied by tau squared, this version.
What?
Exponent.
Yeah, omega square tau square.
No, extra tau squared multiplied by
There's a
exponent.
tau square.
Here.
Yes, yes.
No, right, but since it's exponential will kill everything. Yes, yes. So I just put all this here. I don't want to discuss. Okay? What I want to say is that if you have very large, then you have an exponential suppression. This is the other limit I was mentioning before. So if you do the changes slow enough, then the system remains in the ground state. The probability to go to the first excited state becomes smaller and smaller. Okay? So this is what we would call adiabatic limit. Okay? So you change, so the Hamiltonian is time dependent, but the changes are so small, so slow, not small, so slow, that if you prepare the system in a given eigenstate, the system will adjust to the instantaneous eigenstate. So you do not produce excitations. So we will study the adiabatic expansion in details, but this is a first good example of that. Okay. Now, today, I would like to describe another very important case of time-dependent perturbations, which are periodic perturbations, periodic in time. Okay? You will see that we are going to get to the point in which we understand what we discussed in the previous lectures about, you know, resonance, so transition between levels, and we see when the transition is allowed or not. So, we will consider, say, some perturbation So suppose that you have certain matrix element. I want to write directly in the matrix element of the unperturbed Hamiltonian. So this will change in time as VNM times cosine of omega t. Okay? Now, if you have this perturbation, then you know how to compute the probability to have a transition, right? So we just consider probability. So we solve the time-dependent perturbation theory to first order in the perturbation, and then we get Cn, so the coefficients, okay? That the coefficient tells you that because of the time dependence, then you can have transition to the different level. If you start with a given level, then you can go to different levels. And from there, you can compute the probability that certain levels are occupied. Okay? Now, if you consider this perturbation here, then computing the probability as a function of time, this is something easy to do. And then you will find that the perturbation, let's say, going from I to n as a function of time will be something like Vni squared over 4h bar squared. And then you get two different terms. 1 minus e to the minus, to the I omega ni plus omega t, omega ni plus omega, plus, you get two terms. 1 minus e to the I omega ni plus minus omega. And then you get omega ni minus omega. Okay? So you get two terms. But then you see that if the frequency omega is close to the frequency difference between two levels, there is one term which is much more important than the other. Which one? The second term. So there is a term which is resonant. What does it mean, resonant?
The transitions will be more probable.
So you see that this, you get even a divergence if, okay? Now we should be careful that here we are doing time-dependent perturbation theory. So you cannot get divergence. I mean, a divergence in the probability does not mean much because the probability at most can be 1. So the fact that you get a divergence is related to the fact that perturbation theory is not valid. But what is more important is that when the frequency is close to certain transitions, then the probability to jump to that particular level becomes much larger. Okay? So this is the same. I mean, you remember with the harmonic oscillator, we discussed, I think last time, a few time ago, right? So if you have an harmonic oscillator with a given frequency, proper frequency, and you apply a force, periodic force, with the right frequency that match that of the internal of the harmonic oscillator, then the amplitude will be large. Okay? So this is a resonance condition. So if you want to induce a transition between levels, then you should be careful in choosing the frequency of the incoming radiation. So if you take a radiation which is totally off range of frequency, transition will not be induced because this will not go to the resonant peak. Now, if we forget about this term, we just consider only resonance terms, then this becomes equal to V and I square over 4 h bar square, and then you get something like sine square omega n I minus omega t over 2 divided by omega n I minus omega over 2 squared. Okay? So do you know which kind of function is this?
Which kind of function?
I mean, how does it look?
One and
So you have a big peak at the small t, and then you have wiggles which are suppressed, right? Now, if you choose the frequency right at the transition frequency, how the probability changes in time?
well, we just Taylor expanded it.
Yes, do it.
Like t squared.
Yes. So this goes like t squared. Okay? Now, what does it mean? So, you see that if you do this expansion, then this expression is only valid when t is sufficiently small. So obviously the probability cannot become larger than 1. Okay? So, if you want to consider this as the probability as a function of time, when you are on resonance, then this is also the limit of applicability when you consider small times. Okay? So again, when you consider time-dependent perturbation theory, then in some cases the result that you find is only valid in certain range of times. Okay? Now, I would like to make a step further, and is this clear or not? Okay? Because otherwise you get nonsense. It cannot be, for instance, here you get the probability becomes much larger than 1, which is something which is clear wrong. Okay? If you are off resonance, since you are not able to excite atoms, and probably the validity of this expression may hold for much larger times or arbitrarily large times. Okay? So in time, when you consider time-dependent phenomena, then not only the various energy consideration should be taken into account, but also the range of time interval where the perturbation theory is valid should be taken into account. Okay? So I would like to still discussing about this. Then I would like to consider a bit more careful the resonance condition. Okay? The resonance condition And I would like to introduce a very important concept, which is and the corresponding result, which goes under the name as Fermi golden rule. Okay? Do you know Fermi golden rule? No. Should we wait for just let's wait for a second. So Fermi golden rules. I just tell you a few things, but then we do the step one. So Fermi golden rule essentially tells you, it's an important result which tells you how to compute the probability per unit time that a quantum state can have a transition from one state to another. Okay? So, in the next thing, what I'm going to discuss is the probability per unit time. Okay? This is important. Now, so I'm going to consider the situation in which the system is on resonance. Okay? So I just want to consider essentially on resonance system. Now, on resonance system means that an M, so e to the I omega t plus e to the minus I omega t divided by 2. Okay? This means that this first term here relates to this, and this first term relates to this. Okay? So if I'm on resonance, we agree that I can forget about this term here. Okay? So when you are on resonance, essentially, this means that you can consider just perturbation, which are e to the I omega t. Okay? I have a very nice assignment at the end of the lecture. Okay? You will enjoy. Okay? Now, so since in the notes it's done like this, I would like to consider a perturbation which is like this. H equal to H0 plus V e to the minus I omega. Okay?
And also saying that V is a Hermitian operator. Because if we start this way, generally V and M has to be
Now,
Hermitian.
if you don't, yes, V should be Hermitian.
So this is not.
No, V is not Hermitian. I mean, yes, you're right. So let's do it this way, okay? So I just want to keep this and forget about the. So there are ways to do it, but then I have to put condition on V or something. The only thing I would like to say here is that I just drop counter-rotating terms, okay? This is the only thing I would like to do. So you are right that this is not Hermitian. I'm simply forgetting this term, okay? And the only thing I would like to do, okay, so if you want, let's do this way. Okay? So probably this is better. So I just consider this situation, okay? So I just do the following, and then I drop the off resonance term, and I consider this, right? So we are happy. Now, what is the probability that the system will have a transition? So the probability or resonance. The probability that the system has a transition is just this one, T(I)n as a function of t. So this is all resonance, okay? So I choose, and I remove this factor 4 because I just multiply by 2. Something else I would like to do is just multiply by pi over t and divided by pi over t. Okay? This is what we found before, but I consider this. So now, if you take this function and you do the integral over, so if you take sine square x over 2 over pi t x square, okay? So x is just the frequency. So if you do the integral over this, over dx, this is 1. Okay? So you can see that if you take t to infinity, then this becomes a function which is very peaked only when x is equal to 0, with an integral which is 1. So when t is very large, then we can approximate this object as a delta function. Okay? So this can be approximated as a delta function of omega n I minus omega. But then what is nice is that this is the probability. But if I want to know the probability per unit time, oh sorry, I forgot this, the factor 2. Yeah. Okay. When I take the probability per unit time and I call it rate, okay? Rate, which is the probability rate to go from I to n over time. This is nothing else than this, 2 pi it's pi vni squared over h bar squared delta of this omega n I minus omega over 2. So this is the probability per unit time, okay, which is the rate. This you can write also with just in a different other form, which is the standard known form. And goes under the name of Fermi golden rule. So let's see this. So this is the probability per unit time that the system goes from one state to another when you consider the system which are driven by periodic potential which are close to resonance. Now, this is just tells you what is the matrix elements which connect the initial and final state. Okay? The energy, total energy is conserved. So, oh sorry, please H bar here. So the system goes from one energy to another, absorbing exactly that quantum of energy. So this is something that you know in words. So to induce a transition from one level to another, you have to give that quantum. So if the frequency is mismatched, then the system cannot absorb, and therefore there is no transition. Okay? So the concept of resonance is exactly, that appears here, is exactly what you know from other sources, from other, coming from other parts. Okay? So there is some energy conservation. Okay? And this just gives you the rate at which you, so for instance, if you start, so for instance, if you want to write a problem in which you have a certain amount of atoms in the ground state and a certain amount of atoms in the excited state, in a given other state, okay? So then you can write some kind of a master equation for the probabilities, okay? So how the probability to be in the ground state will change in time. This will be given, say, P0. The rate, okay, to go from, I don't know, the ground state to all the other levels, okay, times P0. So you have a certain probability and then the rates, and then the system will change its probability, plus then you have R n to 0 Pn. Okay? So from this Fermi-Gordon rule, you can compute various rates. So we discussed again tomorrow, because your face do not look good to me. But the last 10 minutes, I would like to discuss one extra assignment, okay? Consider a system, a spin 1/2 system, okay? whose Hamiltonian is omega 0 over 2 okay? So these are the Pauli matrices. Okay? Then you just put a time-dependent field, okay, which can be written as h bar omega which multiplies cosine of omega t sigma of x, okay, plus sine of omega t sigma of y. Okay, sorry, let's call it delta. Okay. Okay? So, now you have to write down the equation for, so you know that the state at time equals 0 is up. Okay? Now you have to compute the states at any time, let's say something like at up plus b of t down. And then I want to know what is the probability that the system is in down.
This happens at t equals 0, right?
No, y t equals 0. Let's t here.
No. At the negative times, we don't have this time-dependent magnetic field.
No, this is not, I mean, you want to start the evolution, we don't know what it is. Okay, so you're starting in this situation, okay? So there are two things I should tell you, because otherwise it's too difficult. Now, the first thing you have to write down the Schrödinger equation, you have to translate for a couple differential equation for A. So you have to write the Schrödinger equation, time-dependent Schrödinger equation for two components, A and B.
Is the second equation get side of the evolution of the
This one?
term?
No, there is no perturbation. This can be solved exactly.
Okay.
This is what I want to say. I did not say yes, you have to solve it exactly. So first you have to write down the equations. Then you have to think hard, because you have to find a transformation that simplifies a lot the problem, so that it becomes a time-independent problem. I can tell you, if you write down explicitly this, then basically you have to find a reference frame which is rotating, such that the system looks like a static magnetic field. If you do this, then the problem becomes very easy. You two do not look for the, okay, so you already found the page in which this problem is solved, okay? No, I will, next faculty meeting, I will propose that you don't have any more access to internet, so. No, seriously, try to do it, because if you succeed, then this is great. Once you do it, then it becomes very easy. Okay? So see you tomorrow.